talking a little bit about some a little more real worldish kind of stuff here. Speed, velocity, accelerations, and such things like that. So if you would, let's see how much you remember or maybe just already know about this stuff. If you can try to define what you think velocity is. Same with speed. There's a little fill in the blank. And then I hope those last two statements for the veterans in the class, you're like, ooh, I've done that before. I know how to relate these things together to get to that. And I'll help you with these in a second. I just want to see how much you remember, see if you can put it together. Warm up. Then we'll do a question. Or a series of questions, actually. So, I know where Julia is. It's 2/11 of you. 18 Anybody have a thought on what velocity is?
It's a vector.
Velocity is definitely a vector. That will become, that particular perspective will become more and more important throughout the year, for sure. Velocity is a vector.
Displacement with relation to time.
Yeah, okay. So we could also say displacement divided by change in time. That'd also be accurate. Can anybody expand on what displacement is?
The distance away from the original position.
Let's try not to use the word distance when we're defining displacement, because that could be a little confusing, I think.
How far something has moved into the original position.
Yeah, how far you have moved from your original position. I like that. Can anybody express what Meg just said, which is very good? Can anybody express that using a little more just math? Because we can say it a lot quicker with math. Delta X, and with X standing for what? Position. Yeah. So yeah, you could say delta X over delta time. You could say delta Y over delta time. I mean, just whatever the position variable happens to be, the change in that divided by the change in time would give you velocity. Yeah. So in Calc AB and probably pre-calc, it was all one-dimensional motion for the most part. In this class, we're later on, not right now, but later on, we're going to release it to also not only move left and right, but up and down all at the same time. And if you ever take Calculus 3, not only will it move left and right and up and down at the same time, it'll move towards you and away from you and up and down and left to right all at the same time, called a vector-valued function. And it just gets a little bit more realistic, right? Because things can move in 3 dimensions for the most part. And so we're going to build a little more realism into this. So speed. Anybody just maybe use some words or some thoughts to define speed?
No particular direction.
No particular direction? Say it again.
Absolute value of velocity.
Well, that's this right here. The speed function is the absolute value of velocity function. Yep.
Isn't it also the magnitude?
There we go. That's the word I was looking for. The magnitude of what?
The vector.
Let's call it magnitude of the velocity vector.
Yeah.
And so, like you just said, Jack, we're essentially just taking the amount from the vector and ignoring the direction. So for us, and also tying in with what Santi said, since, if we have some object moving left and right, whatever, maybe up and down, and we neglect the direction, right? We just ignore the direction. Doesn't that mean that speed has to always have the same sign?
Mm-hmm.
It's got to be positive, and that ties in pretty well with the speed function being the absolute value of the velocity function. It's going to be non-negative, right? It's either going to be 0 or positive, no matter what. Okay, so speed is increasing when? Do you remember this, veterans? We hope Jack maybe he already knows it. Say again.
Signs are the same of velocity and acceleration.
There you go. Yes, acceleration and velocity have the same sign. And so this applies for when velocity and acceleration are both positive, and it also applies when acceleration and velocity are both negative. If they have the same sign, then we have a situation where the speed is increasing or the object is speeding up. So then the speed would have to be decreasing when what would happen? What would be the conditions? Different signs, yeah. Nick, I'm sorry I caught you right there in mid-bite. If they have different signs, so if one of them is positive, the other one's negative, or vice versa, right? Okay, so hopefully that either A, makes sense, and or you remember it. B. So both would be good, right? Yeah. Okay, so let's see if we can apply some of these thoughts with our example coming up here. This lovely piecewise graph. Which, believe it or not, I think is continuous. That's what the plus pi squared plus pi is all about on the second piece. I think that makes it continuous. Yeah. Anyhow, so if y'all would see how many of these you can do. See how far you can get with this. Wants to know what is the position of the particle at t equals 1. Find s prime of 5 and explain what that means. So on and so forth. We'll get into that speed increasing or decreasing part there with D and E. So do as much of this as you can. We'll get some answers up there kind of as we go. I'll just be around to help or just ask questions as you're doing this. Do you need a calculator here? I don't know. You might. I don't think you really do. I don't know. Whatever you think. For A, I've peeked over a lot of shoulders and I've seen this, S of 1 equals 2. Seen that a lot? That makes sense to you guys? You got to pick the right piece depending on the domain, right? So hopefully you pick the piece that went with the 0 to pi part, since 1 is in that interval. Okay, just wanted to check in with you on that. Keep going. We'll look for some other answers here in a minute. So again, just walking around, I'm seeing a lot of folks that have something like that for B. Negative of 2 pi plus 1 cosine of 5. Sometimes people will forget that pi squared and pi are both constants, so their derivatives would be 0. Anyways, so there's a thought about got a numerical answer up there for C. Sure, looking around. Most people have that.
Why'd you say 2?
Oh, because I'm an idiot. No. We can be idiots together.
Find the derivative. Okay, definitely find the derivative for T.
So let's see. That guy is still right. This one's.
Okay, we'll discuss D and E here in just a minute. I would love to hear your thoughts on B. What do you think the meaning of B is? Like, what is that? Velocity at t equals 5? Yeah, I agree. So this is velocity at t equals 5. All right, and then how about C? What is the meaning of S double prime of 2?
S double prime of 2?
Yeah, what does that mean?
Acceleration.
Acceleration.
That's 2.
Acceleration of this particle, this object, at t equals 2. Yeah, agreed. Okay, so then for D, it says, is the speed increasing or decreasing when t equals 2? Well, remember we have to compare acceleration and velocity signs. And I already have S double prime of 2, and I know that it's positive from what I just found in C. What about S prime of 2?
Positive 4.
Okay, that's 4. Then, yeah, 2 times 2. Yep, that makes sense. Also positive. So if velocity and acceleration both have the same sign, speed is doing what?
Increasing.
Yeah.
5, not 4. It might be 5, yeah.
Is it 2t plus 1?
Yeah, it's supposed to be 5.
Gotcha. Well, let's fix that real quick. You do want to have actual correct numbers, so we'll go with that. Yep, 2t plus 1 makes sense. Okay, and then maybe for E, this is maybe where the calculator came into play, just for relative ease of handling the numbers. So S prime of 5. Meg, you had that decimal, didn't you?
S prime of 5, yeah. Negative 2.066.
Okay, you guys agree with that? I think I saw that a couple times. All right. So then we also have to do S double prime of 5. So this would be, oh gosh, this would be what? Positive 2 pi plus 1 times sine of 5, right? So if you're, question.
Yeah, is S double prime of 2 actually 2? Because I got a different number.
Can I finish this one first? Since we
Yeah.
have momentum, we'll come back to it. So did anybody figure out S double prime of 5? 6.984. Of course, this number is negative. This number is positive. Signs of acceleration and velocity are different. Therefore, what's our conclusion? Speed is decreasing. So make sure you put, therefore, speed is decreasing. Okay, so back to Santi's question. You said, is S double prime of 2 really 2? So let's see here. So we'd have to use this piece here. So S prime of t would be 2t plus 1. So then S double prime of t would be just 2. So I think regardless of input, I think S double prime is 2.
No, I didn't mess it up.
Math fight? No? Yes? Okay. All right. Any follow-ups? Thing in general, the whole question, it covers a lot of ground. No pun intended. Get it? That was golden. Okay. We're good? All right. Awesome. So let's move on then. The topic of the day really is second derivatives and concavity and that kind of thing. There's an intro video here, and I believe example number 1 is kind of the first example that we're just going to jump in here and try. So if you would, see if you can answer this question. Determine the open interval or intervals on which the graph of f is concave up, concave down, if you are given f double prime right there. You want to pay really close attention to what you're given and how it connects back to what you are wanting to find. So take a minute, try to figure out example number 1. And Santi, I don't know the answer to your question. I was just taking numbers from them.
Okay.
So they very well could have all been wrong. I don't know.
Okay.
We might want to investigate that a little bit more. Okay. So I'm going to take Forrest's idea. I think a sign chart here is a nice place to start. This is going to be an F double prime sign chart. And so I'm going to put that label over here. I want to make sure that I remember, and I'm communicating what this sign chart even means, because a sign chart could have something to do with lots of things. So I'm going to do this. So I'm going to put those 3 zeros up there. So -2, +1, and 4 are all zeros of f double prime. So those are possible places where f double prime, could change signs. Therefore, the concavity could change. And you can do, I don't know. I think it's kind of nice here. I like to actually give numerical answers. I'll put over here maybe like f double prime of -3 would be something you could test out. And I don't know how difficult this is going to be. It's going to be, I don't know that I would give you something like this and expect you to do this without a calculator and give me numerical values, right? So let's just do this positive, negative perspective and see what we get. So if I plugged in a -3, what's the result of this? What will we get, a positive or a negative? It'll be a negative cubed. What about this middle one? If I plug in a -3, -3 plus 2 is negative, right?
Oh, you made me question my whole life. I was like, oh no, what's he saying?
And how about the very last one? It's guaranteed positive. Why?
Because the exponent is positive.
Fourth, not that it's positive,
Or
it's
even.
even, yeah,
Oh my
guaranteed.
gosh.
So a negative times a negative times a positive is a positive.
Even.
Now, for us, this is where I think we can get a little trickier and navigate our way through this faster. Do you guys remember about multiplicity? Okay, so check this out.
There's 3 zeros at 1.
It's an odd multiplicity, right?
So it
Hey,
goes
Julia.
through versus touching.
Yeah, I want to make sure everybody gets this. Odd multiplicity means that the graph of whatever it is we're doing here goes through. Even multiplicity means a kiss, a bounce, what do you want to call it? Yeah.
I call it kiss.
Okay, that's very sweet. Okay, so -2 has, -2 comes from x plus 2, which has what kind of multiplicity? Even or odd?
Even.
No.
Odd.
There was only 2 possibilities. So what I'm really asking is, what's the exponent on x plus 2? And that number is? So that means the x plus 2 has odd multiplicity. So at -2, the graph of, in this case, f double prime, will actually go through the x-axis and change signs. That's the most important thing we're dealing with here. What kind of multiplicity does the 1 come with? Odd, right? Because that factor is cubed. And so odd, once again, means the graph of, in this case, f double prime, will go through and change signs. But what's going on with multiplicity of the 4?
Even.
It's even, right? We've got an exponent of 4, which is even, and so that's where the graph of f double prime would actually not change signs because it's just going to touch the x-axis and then bounce away or whatever. So f double prime would remain positive over in that interval. And if you want to do all the little test values on each of the intervals to confirm that, you're welcome to it. But multiplicity on these nice linear factors should work out great. Make sense? Okay. So then it does use the magical words justify your answer. And so, Forrest, I think you had most of this, if not all of it, except for the justifying your answer part. So here's how I'm going to tie this up. You got to have what I'm about to write in orange. You got to have this. So I would say f is concave up on these intervals, -infinity to -2 and 1 to infinity.
Well, no, it's not 4.
You can't have concavity. You can't. It's almost like the increasing, decreasing thing. At a single point, you really can't have concavity. It's always going to be over like some at least itty bitty interval. And so, yeah, it really should be infinity. Okay, and then you'd say because f double prime is positive on those intervals. So for us, this is kind of what I'm looking for as far as the justification. One sentence, tell me where f is concave up, and tell me why based on the second derivative. Does that make sense? Yeah. Okay. And then we do the same sort of thing because it also asks for concave down. So f is concave down on -2 to 1 because f double prime is negative on that interval. So be in good practice with your justifications. Make sure you're giving a complete answer with a reason, a correct reason. Okay. So there's number one. Number two, a little bit different. It says the graph not of f double prime or of f, but the graph of f prime is given below. Determine the intervals on which the graph of f is concave up. And it does not say to justify your answer, but let's go ahead and do that anyways, just for practice. Make sure we are reinforcing how you justify your answer on this sort of thing. And it is f prime, so it's a little bit different. So please try number two.
Do we have to use f double prime?
No, in fact, I would highly recommend, for example, number two, that you use f prime to make your reasoning make sense.
So in the cases of x equals -4 and x equals 5, where the point is included in the graph, because it's a closed circle,
Sure.
would I then include that on my interval?
So I put the word open interval here in the instructions to, to just try to make it clear, because I don't want, I don't want that debate to become the thing that you fixate on,
Yeah.
So I really wouldn't mark it right or wrong either way, to be honest with you.
Okay.
Whether you included that endpoint in this case or not, I'm not too worried about it.
Sounds good. I know what's going on. Just that's a very
Yeah.
thing.
And we can talk about the nitpicky things, but as far as how I'm going to assess you, I'm not going to make that the thing that's like, oh my gosh, you would have made an A, except you messed up the whole open and closed, and it's just not. I don't think it's accurate for trying to measure your learning.
Sounds good.
Okay, so has anybody found any intervals for number two where you would say f is concave up? How many intervals did you find? 1, 2, 3, 4, 2? 2 different intervals? Okay. So I will say, come on. I will say f is concave up on, what's your first interval? What do you think? -4 to -1. All right. And you said there was 2 of them, so what's the other one?
2 to 5.
2 to 5. Okay. Yeah. What's the problem? Oh, I wonder if this just died. Because, might have just died. Because why?
Because f prime is increasing on those intervals.
I, Jack, agree. This is really awkward with my finger. On those intervals. I'll just put INT for intervals. Okay. Okay. Jack, well done. Good explanation. Correct intervals. You good?
Yes.
Lovely. Awesome. Okay. So let's talk a little bit about points of inflection. Again, see if you can fill in some blanks here. This is all very conceptual. We'll do an example here where we actually try to find some of these. So I'll try to keep up with you. Point of inflection is a location where the blank changes. Concavity. Yep, that would be an apt description. For the concavity of whatever graph you're looking at, whether it be F or G or H or whatever, changes. So I'm giving you some wordings that are good justifications. So the first two obviously have to do with F prime, which is more closely related to the example we just did. And then the last one is more closely related to the first example we did. And I really think that you might ask yourself, well, when do I use this and when do I use that? Like, how do I decide? I really think, just in my own personal opinion, you should probably use the one that goes with the information you were given. So if you're given information about F prime, you really ought to use one of the first two. If you're given information about F double prime, you probably ought to use the last one. To me, that makes the most sense. I want you to be flexible in your thinking. So here's kind of a tutorial. I'll let you fill in the blanks here. To locate points of inflection, determine the values for which F double prime of X does what? Changes signs. There you go. So you might say, gosh, why are we, kind of repeating this? Some of you will be able to identify with this. Last year, veterans, so many times, I would say, hey, we're looking for inflection points, and where do those happen? And somebody would always raise their hand and say, it's where f double prime equals 0. Happen all the time. Now, isn't that a big hint about where you might get an inflection point?
Yes.
But just because f double prime equals 0 doesn't mean that f double prime changed signs. And so you got to take it out one step further and say that. That's how you can actually find and therefore justify. Also, it's these inflection points happen where f prime changes from blank to blank or blank to blank.
Increasing to decreasing or decreasing to increasing.
I agree. You said it so well. All right. Okay. So with those concepts and ideas in mind, and by the way, there are so many cool little ways of looking at the answer to the question of well, why? Tell me about the graph. Why would the graph of this correspond with this pattern of behavior? There are so many things. Part of it's covered in the intro video, but if you have some follow-up questions, we obviously don't have a lot of time in here to explore all that, which is unfortunate, but it's just a fact of the matter. Come talk to me, and there's all kinds of little graphical ways we can look at things, and it's all, I think it's personally kind of cool. And if you have some questions like that, just let's find some time to talk. I'm mildly sad that we don't have time to really camp out on that. Okay, so then right here says find the points of inflection and discuss the concavity of the graph of f. And you're given a function for f. So you're going to have to do a little bit of work to get down to the nitty-gritty details here. See if you can figure out how to describe what's going on here. And I forgot to do attendance. I would say no calculator, yeah. I think, let's see see how easy it is to solve the resulting functions that show up. Hopefully they're solvable without a calculator. We'll see. One of the sad facts of our new schedule is we have to skip this thing called Newton's method for solving equations. It is a really awesome method where you can take some equation that there are no rational roots for it, and you can use derivatives and all kinds of things to estimate the answer to an equation to any degree of accuracy you choose. Just cycle it more. Just keep cycling and cycling and cycling through this little formula. Kind of a cool thing. So to answer your question, is this calculator active? You ever thought about what on earth is my calculator doing when I ask it to find the zeros of some crazy equation? It's using an algorithm like
what's wrong with execution?
That's just weak. It's it would be like if our football team scheduled a game against the local 8th grade team.
So pooter, basically.
Something along those lines, right? It's
I gotta play pooter like that.
what are we doing?
Respect on pooter.
There's no challenge here.
But that's why you make
Santi, I have so much respect for you. I don't want you to lower yourself down into the gutter of calculator shortcuts.
I'm surprised you made it this far with respect for him still.
Well, there's still a whole year left, right?
Thank goodness I guess you've only seen
You are
him
a
in
faithful
class,
person.
so
And Santi, they just
rip on you.
Might
Yeah.
not be about
they're
this.
not throwing you under the bus. They're throwing the bus that you're under another bus. You're stuck.
It just never stops.
It's like the second
every
derivative
class
of
we
bus
You're
throw.
really stuck.
That's just what happens to shining stars.
Make them burn out and crumble.
Wow.
Did you ever get one of those?
So you drop your shoulder
I used to drop it.
at this 130 pound child. How tall? How small is he?
He was so small.
He was your size.
Okay, so I'm kind of curious. When you were looking for points of inflection, did you guys go to f prime or did you take it all the way to f double prime?
Because it was such an easy.
I think double prime makes it way easier, doesn't it?
Heck yeah.
Because you could get into that f prime thing, but to me f double prime makes a lot of sense. So f prime equals 6x squared minus 6x minus 12. F double prime then equals 12x minus 6. I really don't think we'll need a calculator for this, right? Pretty easy equation to deal with. And so if I'm going to try to find Points of inflection and concavity stuff going on. What do I need to do with f double prime to get me started?
You gotta find the zero.
Got to find the zero or zeros. Yep. Did you all get x equals 1/2? Now, is that enough right there to say, oh, therefore we have a point of inflection?
Because that might.
Might be a bounce or a kiss, right? We don't know.
Let's call it.
Yeah, we'll go with bounce. So I think maybe we go with Forrest's idea again, right? The sign chart is a nice visual. So if I plug in a 0, f double prime of 0 is -6. F double prime of 1 is +6. So I get a negative interval there, a positive interval there for f double prime. Is it frozen again? I thought I unfroze it. Oh, I don't know how that happened. Weird. There it is. Sign chart deluxe. Okay, so then do we actually have an inflection point at x equals 1/2 like we thought might be true?
Absolutely.
We do. So I'd say because f double prime changes from, be specific here, negative to positive at x equals 1/2, f has its inflection point. As an AP reader, I get all kinds of things like inflection point, infection point, all kinds of stuff. Yeah, we do. We're like, yeah, you just misspelled it.
Yeah,
That's
I'm
awfully
not
generous of you.
concerned about like what.
There are some limits to that where they're like, that's just too much. We don't know what the word is anymore. So then f is concave up where? On what interval?
1/2 to infinity.
Yep, on 1/2 to infinity. Because f double prime is positive, f is concave down on negative infinity to 1/2. Okay. So again, hoping this is flowing and making sense and rememberable for those that have it in their brain somewhere already. Doing okay?
Yes, sir.
Okay, we are going really fast. Last year, we took the better part of like 4 or 5 days to go over all this that we're covering in like a day and a half. So we're going much faster. Okay,
Wait, are you saying like an AB we did that, or are you saying last year?
AB. Yeah, for the AB veterans, we took like a good solid week plus to cover all this stuff.
Sounds about right.
We're doing it much faster. Okay.
Yeah, we're going on.
So then the other piece to this puzzle is another way to use the second derivative to help us inform us about maximums and minimums, like relative maxes and minimums. And so this is a pretty handy tool. This, depending on the situation, can be a little faster than the first derivative test. The function of the second derivative test is the same. We're trying to find relative max and mins. Like that's the end result. How we get there is a little bit different, but same end result. So let me just remind you of this, or you can remind yourselves. What are the candidates for relative mins and maxes?
Critical numbers.
That's right. Critical points only, right?
Endpoints on this.
So we're looking for relative min or max. We don't consider endpoints at all because there probably aren't any. So critical points are places where what equals 0 or DNE? F prime. Now, later on we're going to use the second derivative to help us clarify where the mins and maxes are. But the mins and maxes, relatively speaking, are going to be at critical points where f prime is 0 or DNE. So sometimes people get a little confused and they're like, oh, well, we're supposed to use the second derivative test, so maybe I should be setting f double prime equal to 0? No. If you're looking for relative mins and maxes, you're looking for critical points for your candidates, and that's where f prime is 0. What we do with it later, something different entirely. So here we go. If I'm going to try to find the critical points, I need to find f prime. What would you guys say f prime is for this one?
3x squared minus 10x plus 7.
I agree. Ooh, this is going to test your factoring skills. We're going to set that equal to 0. I know that DNE is not a possibility here because that's a polynomial. So I'll just set this f prime equal to 0. We need to solve this, and yes, I would definitely expect to be able to do this without a calculator. Does anybody have the factoring? Or I suppose you could just use the quadratic formula.
7. Oh, no, it's 3x.
Times,
It's 3x
7 and
minus.
1.
So-
No,
It's
no.
3x minus 7, 3x, and then x minus 1.
If you ever have any doubts about this, can't you just like multiply back out in your head real quick and just double check the middle term? That's what I would do.
Oh,
Okay.
Use the square like a dork.
So then, did y'all get x equals 7/3 and x equals 1 as a result?
I don't want to hear it.
Okay. Now, let's make sure we understand what these things are. At this point, we could label these and say these are the critical numbers or critical points. Yes. These are our candidates for the relative mins or maxes, and we haven't yet figured out exactly which one is which, or maybe one of them is a neither. We don't know. So then we could use the first derivative test. Forrest's idea of the sign chart would work great here with the first derivative test. But you were asked to use the second derivative test. So what's your next step?
Find the second derivative.
Find that. Yeah, find the second derivative. So I'm going to come over here and say f double prime equals 6x minus 10. And this is where the second derivative test is a little more convenient, because what do I do with that second derivative?
That'd be plugs, right?
I just plug what in?
Plug the points in.
Yeah, take the critical points and just plug them straight in to that second derivative. So I'll go f double prime of 1. And what would that equal if I... -4. So I'm gonna write a little bit more than I would normally do here, just to clarify some things. What's the most important thing about that number?
Negative.
It's negative. Okay. Therefore f is what?
Concave. It's a down.
Concave down. Yep. Therefore, at x equals 1, f has what? A relative max. You can picture concave down. I'm making the hand motion here. Concave down. Aren't you going to have a max up there at that critical point? I like your hand motions too. Yeah, little mountain there. I like it. So then I would also say f double prime of 7/3 could be calculated as well. What would that be?
14.
4. No, I think it's 4. 14 minus 10, right?
That's what I meant to say.
That teen just slipped out. I get it. So therefore, f is concave what?
Up.
And if we have a critical point at a place where f is concave up, what do we have? A relative min. I want to make sure that that logically makes sense. You could picture the graph and put it all together and come up with at x equals 7/3, f has a relative minimum. Okay. What do y'all think? Okay, that's good. So I think what we will do, let's see here, I see you all tomorrow, right? Yes, I do.
Yes.
So I think tomorrow we will use example 5 as kind of a nice tie-in between the 2 days. We'll use that as a little warm-up, and we'll be into limits as x goes towards infinity tomorrow. So hope you all have a good day.
Me too.
Enjoyed working with you. Enjoy the rest of your classes.